Hi, this is Kandai Watanabe from CU Boulder, and I'm presenting my work on optimal planning for time partial order. This is a joint research with Toyota Motor North America. Increasing efficiency is crucially important in many domains for manufacturing to administer processes. These processes are called workflows and often imposed with precedent and timing constraints. To clarify this, let's look at the aircraft turnaround example on the right. We might have constraints like passenger can only deboard after stair truck is placed, or unloading luggages takes at least 15 minutes. In previous work, we proposed a succinct and interpretable representation of such tasks. We call it time partial order. We show that these models can be learned from data very efficiently. In this work, we focus on planning for robots, giving a task specification as a TPO. TPO models specifications with nodes representing the events and edges representing their partial orders. Clocks represent timing constraints. Clocks act like a stopwatch and can be reset and measure local time. Giving a TPO, how can we come up with optimal plans for robots in this environment? The problem in this work is to find plan or plans in the environment that minimizes the end time subject to the TPO specifications. We're interested in synthesizing plans for both single and multi-robot settings. Our approach is to abstract the motion of the robot as a transition system represented with nodes and edges, and associate each event in the TPO to the state in the DTS. Now the problem is to find plans that visit each event just once with respect to the precedent and timing constraints. For a single robot, we can view this problem as a generalized traveling salesman problem with time windows and precedent relations. There are many existing work to solve TSPs, including exact and heuristic approaches that we can leverage. To construct the TSP graph, edge costs are computed via shortest path algorithms between the states associated to the events. To solve this problem, we can formulate a mixed integer linear programming to find the optimal plan that visits each event just once. The formulation represents the edges as integers and restrict only one incoming and outgoing edges to be active. This allows the MLP solver to find a sequence of active edges that minimizes the make span with respect to the TPO constraints. We can handle duplicate event labels if we formulate it as a generalized TSP. This is useful when the same task can be completed at multiple different states. We can easily extend it to multiple robots by augmenting the initial states. To illustrate the effectiveness of the approach, let's go back to the aircraft turnaround example. Here, the task is to complete the aircraft turnaround with 3 Jackal robots and simulating the ground staffs. The robot on the right first brings the conveyor belt next to the aircraft to start unloading and loading, which takes some time, so it will stay by the aircraft. The bottom left robot is in charge of the catering vehicle. However, the catering can only be started after the stair truck is placed and deboarding is completed. So it will also wait for some time to start and complete the catering service. Let's rewind the video to see the robot on the top left. On top left, the last agent brings the stair truck and immediately heads to the refueling vehicle to start refueling. The refueling can be completed unattended, so the robot lets the other robot on the right to handle moving out the vehicle later. After loading is completed, the bottom right robot moves out the conveyor belt and subsequently heads to the refueling station to move out the refueling vehicle. After all services are completed, the top left robot moves out the stair truck and they all go back to the depot locations at almost the same time. To test the scalability of the approach, we run a benchmark by varying the number of nodes. X-axis represents the nodes, and Y-axis represents the time. Color corresponds to the different number of agents. As the number of nodes increases, the complexity increases as MLP is exponential in the number of integers, or in this case, edges. However, the time complexity did not increase as the number of robots increased. We also compared against the operational research tool called OR Tools developed by Google, which contains many state-of-the-art TSP heuristic solvers. Interestingly, the OR tools did not perform well compared to MLP. This is because the heuristics are disabled when unexpected additional constraints such as local timing constraints are added. Instead, they use constraint programming to solve this problem, which is slower than the branch and cut method employed in the MLP solver. Lastly, the algorithm easily scaled up to 80 states as shown in the figure. We further ran the analysis with a timeout of 30 minutes, and MLP was able to solve up to 160 nodes and 40 robots within 30 minutes, whereas oral tools timed out in many cases. Next, we introduce a method to analyze the robustness of the generated plans with respect to the delays. That is, if a robot is delayed, can we still satisfy the timing constraints of the TPO using the same plan? If so, by how much? We introduce a uniform bound epsilon that bounds delays across the nodes in the tour. To find such epsilon, we formulate a linear programming that maximizes the epsilon that is bounded by the smallest delta or delay allowed at each node with respect to the TPO constraints. Here we show the normalized uniform bound divided by the make span for each tour by varying the number of nodes to visit in the grid world on the right. We can see that the bound gets smaller and smaller as the number of nodes increases. This shows that the tours are not robust across most of the cases. This is because MLB minimizes for the make span tau and so minimizes the time spent at each node. If you know such epsilon beforehand, it is easy enough to add the constant to the MLB formulation. However, further analysis is needed to make the tour more robust. In conclusion, this work fills the gap of plan synthesis for multi-robot systems under complex tasks with time and ordering constraints. In our previous work, we showed how TPOs can be learned from data. This work closes the loop of learning and planning going from data to plans. We also show that our algorithm can be scaled up to 160 tasks and 40 robots that can be computed within a few minutes.